Hello, I hope you are doing well. In this video, we are going to cover binary ionic compounds. So we're going to look at ionic compounds that are formed between two different types of atoms. In the next video, we'll incorporate polyatomic ions. So in today's video, we're going to look at naming ionic compounds or naming binary ionic compounds, and then writing formulas for binary ionic compounds. So let's start with a little overview on bonding. So a chemical bond is going to be a strong attractive force between atoms. And in the first couple videos, we'll look at ionic bonding, which is going to involve a transfer of electrons. And then in the third video, we'll look at covalent bonding, which is when electrons are shared between atoms. So why do atoms combine and form chemical bonds? A primary reason is for stability. So recall that our most stable group on the periodic table is group 18, our noble gases, and they're stable because they have a full outer energy level. So let's take, for instance, a sodium atom and a chlorine atom. Recall that sodium, which can be found in group 1, is going to have one valence electron. And chlorine, on the other hand, will have 7 valence electrons. So what's going to happen here when sodium bonds with chlorine is that sodium is going to give up its valence electron and become a positive ion, and chlorine will take that valence electron, so it can then have 8 valence electrons and form a negative ion. So again, sodium would give up a valence electron and form a positive ion, and chlorine would take that valence electron from sodium and form a negative ion. So our ionic bonds are going to be formed between oppositely charged ions. Some of the atoms are going to want to lose electrons, such as sodium, for instance, would want to lose electrons or an electron. And some of our atoms are going to want to gain electrons. Now, when those atoms either gain or lose electrons, recall that that's what's called ions. So there will be these charged atoms or ions. And we're going to have two types of ions we'll look at. We have cations, which are going to be the positive ions, and then anions are the negative ions. So cations are going to be what type of ions metals will form. And then our nonmetals are going to form anions. So recall on our periodic table with our lesson on periodic trends that as we move across a period, so the metals, which again we find on the left side of the periodic table, and the nonmetals, which we find on the right side of the periodic table. So as we move across a period, so from the metals over to the nonmetals, our ionization energy increases and our electronegativity increases. So the nonmetals are going to be, they're going to form anions, they're going to take electrons, and the metals are going to form cations, they're going to lose electrons. And one way, it's kind of silly, but one way you can keep these two terms separate from one another, or that you can remember which ones are cations, which ones are anions, is that cats have pause, so cations are positive, and then a lot of students in the past have said that anions, like, it kind of looks like onions, so that's how they remember that anions are negative ions. So we're going to have these oppositely charged ions, and remember that opposite charges attract, so these ions are going to attract one another, and the number of electrons that is lost is going to be equal to the number of electrons gained. So our ionic bonds are typically going to occur between metals and nonmetals, And like I said before, tomorrow, or sorry, not tomorrow, in the next video, we'll look at incorporating polyatomic ions. And then when these ionic solids are melted or when they're dissolved, they can then conduct electricity because you'll have these ions that are free to move around. And ions, since they have a charge, you have these charged particles that are free to move around. Now, our ionic solids are going to be very strong solids, and they're generally going to have very high melting points. And some examples of our ionic solids are going to be sodium chloride, NaCl, and magnesium oxide, MgO. All right, so before we can name ionic compounds or write the formula for ionic compounds, we have to know the charges that most of our atoms will, or some of our atoms at least, will form if they were to become an ion. So we're going to look at our oxidation number. Now, oxidation numbers are similar to the charge of an ion, and these rules for oxidation numbers will get more complicated if you were to take future science classes. But for this video, we're just going to look at the common oxidation numbers of some of our atoms. And these oxidation numbers are going to represent the number of electrons that are gained or lost. And we are going to get these rules based on the group that our atoms are in. So recall that we can use the group that an atom is in to determine the number of valence electrons these atoms have. So let's look at group 1 first. Let's take, for instance, sodium. So sodium, if we were to look at its Bohr model, so we have Na, and we have our protons and our neutrons in here. And since sodium is in the third period, remember it would have 3 Bohr rings around it, 3 of those electron rings, or electron energy levels. In the first ring, we'd have 2 electrons. In the second one, we'd have 8. And then in the third one, our valence shell, we would have 1 electron for sodium. So recall also, again, that our most stable group of atoms or elements are going to be the noble gas family over here on the far right side of the periodic table. And they're stable because they have those full outer energy levels. So they're going to have 8 valence electrons, of course, with helium being an exception and having 2 valence electrons. So let's look at sodium. It wants to be stable. So in order for it to be stable, is it going to pick up 7 valence electrons? So it will have 8 in its third energy level. Or would it lose the 1 electron it has in that third level, and then it would then have 8 in this second level? So do you think it's easier to add 7 electrons or lose 1 electron? Definitely lose 1. So if sodium lost 1 electron, it's kicking off 1 negative charge. What charge is it going to get when it becomes an ion? A positive 1, right? So elements, in our group 1 are going to have a positive 1 charge, or really in chemistry when we write our charges, we write the numerical value first and then the plus or minus second. So we're going to say they form 1+ ions, group 1 does. Okay, now let's look at group 2. So say we are looking at magnesium. Magnesium, like sodium, would also have 3 energy levels if we were to draw its Bohr model. In the first principal energy level, we have 2 electrons. In the second one, we have 8. And then the third one, we have 2, because magnesium has 2 valence electrons. So would it be easier for magnesium to pick up 6 electrons or to lose the 2 it has here? it's definitely going to lose those 2 valence electrons. So if it's kicking off 2 negatives, what charge is it going to get? A +2, right? Or for chemistry, a 2+. All right, and then we're going to skip over our transitions because they have variable valencies, so they can have variable oxidation numbers, oxidation states. Okay, so we're going to skip them and then move on over here to the boron family. So really for our ionic compounds, we want to look at aluminum on down. So if you were to think about aluminum, it would have 3 valence electrons. So would it be easier for it to pick up 5 more electrons or to lose the 3 valence electrons it has? Definitely lose the 3 valence electrons it has. So if it's kicking off 3 negatives, what charge is it going to get? A +3, right? Or for our case, a 3+. Now, moving on over to the carbon family, this one is smack dab in the middle in that it has 4 valence electrons. So really, the main ones that we're going to look at for participating in ionic bonding are going to be tin, Sn, and lead, Pb. Now, tin and lead can have 2 common oxidation states, 2 common oxidation numbers, and that's going to be a 4+ or a 2+. Okay, so from the carbon family, we're looking at tin or lead, and they can be 4+ or 2+. So moving on over to the nitrogen family. Nitrogen would have 5 valence electrons. So in this case, do you think it would be easier to add 3 valence electrons or lose 5? This time it's going to be easier to add 3. So we're adding 3 negatives now. So what charge is would nitrogen or phosphorus get? A -3, right? Or 3-. All right, moving on over to the oxygen family. They have 6 valence electrons. So would it be easier to pick up 2 or lose 6? Pick up 2, right? So we're picking up 2 negatives. That means they will get a 2- charge. And then looking at our halogens here, they have 7 valence electrons. So pick up 1 electron or lose those 7. They're going to pick up 1 and get a 1- charge. And then what charge would our noble gas family get? 0, right? They're not going to participate here in our ionic bonds or ionic compounds because they are already stable. All right, so let's do a little bit of ion practice, like practice writing out these ions before we jump into writing our formulas and then naming our compounds. All right, so sodium, when you're writing these ions, you'll need to write the chemical symbol. So for sodium, that's Na. And then when you write the charge of the ion, you list it as an exponent or a superscript to the right of the symbol. So for sodium, Na, it's in group 1, and remember they get a 1+, or 1s are understood, so you can just put a positive there. So we have Na+. All right, if it was to form an ion. So let's look at chlorine. If chlorine was to form an ion, what would it look like? So we have chlorine as Cl. It's in the halogen family, group 17. So it would get a 1- charge, or we can just put a little negative there. If aluminum became an ion, aluminum is Al. It's in group 13. So it would have a 3+ charge. And then phosphorus, if it was an ion, so we'd have P, and it's in the nitrogen family, group 15. So it would get a 3- charge if it was an ion. All right. So first, looking at the ionic formulas. When you are writing these formulas, I would write out each ion and then making sure to put the cation first. So the cation, or our positively charged ion, for this video it's going to be our metal, and when we incorporate polyatomic ions it could be ammonium. We'll look at that, poly. But you'll put the cation first, and if you're going off of the name, if the name is correct, it should be the element that's listed first. So your overall charges have to give you 0. In order to do this, so if the charges cancel, like if you had a 2+ ion and a 2- ion, those charges would cancel, so you would just write these symbols. If the charges do not cancel, so let's say you had a 2+ and a 1-, those won't cancel, so you would crisscross the charges to make them subscripts on the partner element or partner atom. Okay. And if you are looking at metals that have variable oxidation numbers, so our transition metals, you will use, or the Roman numerals that will be given to you will tell you the charge. And then if these subscripts can be reduced, then reduce them. Okay, so let's look at potassium chloride. So first off, how can we tell this is an ionic compound? Well, potassium is a metal, and then chloride, when you see IDE, that means you have a monatomic ion. So in our case, IDE means monatomic anion, I should say. So that means it's coming from the periodic table. It's not one of our polys, which we'll look at in the next video. So potassium is a metal. Chloride, which means it's chlorine, is also, or chlorine is a nonmetal. So we have metal and nonmetal, which means we have an ionic compound here. So writing out the formula, we have potassium is K. It's in group 1, so it gets a 1+ charge, or we can just put a positive because 1s are understood. Chloride, which is telling us from the I, means chlorine here. So that's Cl. It's in group 17, so it gets a negative charge. Now we determine, do we crisscross or cancel? So we have a 1+ and a 1-. Those charges would cancel, so we would just write the symbols mushed together and get KCl. All right, looking at this second example here, we have copper 2 chloride. How do we know it's an ionic compound? Copper is a metal, and chloride, again, we see that I, so chlorine is a nonmetal, so metal and nonmetal, that means we have an ionic compound here. So copper is Cu. Copper is in the transitions. So for the transitions, you'll need these Roman numerals here to tell you the charge of the transition metal. So this is Roman numeral 2. So that means it's a 2+. And we know it's going to be a positive because copper is a metal. Remember, our metals are forming cations, positive ions. And then we have chloride. So that's chlorine, and it has a negative charge there. So here, do we crisscross or cancel? Well, we have a 2+ and a 1-. Those aren't canceling, so we crisscross them. And what I mean by crisscross is just the numerical value, so not the positive or negative sign, but just the value is crossed down to be a subscript of the other ion. The other atom, if we're looking at binary ionic compounds, or we'll look at crossing when you have polys in the next video. So there's an understood 1 here. It gets crossed down to be a subscript with copper. There's a 2 here. It gets crossed down to be a subscript with chlorine. So that means we have CuCl2. All right. Let's look at another example here. So calcium oxide. First, how do we know it's an ionic compound? And the reason you want to ask yourself that is because when we start adding in covalent compounds and then acidic nomenclature, they're all going to have their own nomenclature rules. So in order to name one of the compounds you could see, you'll need to first identify, is it ionic, covalent, or is it an acid? So we know it's ionic because calcium is a metal, and this I tells us this is oxygen. Oxygen's a nonmetal, so metal, nonmetal, therefore ionic. So calcium is Ca. It's in group 2, so it would have a 2+ charge. Oxide, again, is oxygen, and it gets a 2- charge. So from here, we have a 2+ and a 2-. Do we crisscross or cancel? Those would cancel. So we get CaO. If the charge is canceled, just mush together the symbols there. All right, so then this next example here, we have iron 3 oxide. So how do we know it's ionic? Iron's a metal. Oxide, that I tells us it's oxygen. Oxygen's a nonmetal, so metal, nonmetal, therefore ionic. Iron is Fe. It is a transition, so we will need to know, or we'll need this Roman numeral here to tell us the charge. So this is Roman numeral 3, so it means it's a 3+. And then oxide, oxygen, and it has a 2- charge. Now from there, do we crisscross or cancel? We have a 3+ and a 2-. Those won't cancel, so we got to crisscross. Remember, just cross the numbers, not the positive or negative sign itself. So we have Fe2O3. Okay. And really the reason for crisscrossing here is, again, you need the total compound, like the oxidation numbers, to add up to give you 0. So if we have iron and it's a 3+, we have this +3 kind of charge or 3+ charge, and then if we have an oxygen and that's a 2-, so those aren't adding up to give us 0. So if we were to add on another oxygen ion here, we have a total of 4-. That's not canceling with the 3+. So now we add another iron 3+. So now we have this 6+ and 4-, or +6 and -4. That still doesn't cancel. So if we added in another O2-, we have 2, 4, 6- and 6+. So now those charges are canceling. And in order for these charges to cancel, we have 1, 2 irons, and 1, 2, 3 oxygens, 3 oxygens. So that's really kind of the purpose of crisscrossing those charges there. All right, and then let's look at one more example too, because remember, if these subscripts can be reduced, you do need to reduce. So let's say we were looking at manganese, for oxide. All right, how do we know this is ionic? Manganese is a metal. Oxide, again, that "ide" means it's oxygen. Oxygen's a nonmetal, so metal, nonmetal, therefore ionic. All right, manganese is Mn. Here, this is Roman numeral 4. So quick little overview on Roman numerals. I is 1. Double I is 2. 3 I's is 3. And then IV is 4. And then V is 5. And VI is 6. All right, so again, since V is 5, 4 is IV, so 1 before 5 or 4. And 6 is VI, so 1 after the 5 or 6. All right, so from here, we have manganese has this 4 charge, so we have 4 plus. And then oxide, oxygen, has a 2 minus. So from there, do we crisscross or cancel? Well, those don't cancel, so we crisscross them. And we get Mn2O4. And now from here, 2 and 4 can be reduced. You can divide both of them by 2. So we're going to, rewrite that as MnO2. So it'd be Mn1O2. Again, ones are understood. All right, so that's writing the formulas. And then going the other way, so writing the names. First, you would write the names of both the elements and put the cation first, or your metal, or if we were looking at ammonium, a positive polyatomic ion. And then if our anion is monatomic, sorry, pardon my spelling, monatomic, that means just one single atom, you change the ending to "ide." All right, if it's polyatomic, you're going to leave it. If your anion is polyatomic, you're just going to leave it whatever the poly is called, but we'll cover that in the next video. All right, so for ions with variable oxidation numbers, we are going to write the oxidation number in parentheses using Roman numerals. And again, our overall charge has to give us 0. So really this is for transition metals. If we have transition metals, we're going to have to write their oxidation number using Roman numerals, and we're going to write that in parentheses following the name of the metal. All right, so let's look at some examples here. NaBr. So first, how do we know it's ionic? Na we know is sodium. Sodium's a metal. Br we know is bromine, and that is a nonmetal. So metal, nonmetal, therefore ionic. So first one here is, again, sodium. And then, is sodium a transition metal? Since it's not, you do not need Roman numerals. So we jump right to the anion. The anion is one single type of atom, just Br. So we take bromine and we change its ending to ide. So we have sodium, sodium bromide. All right, this next one here, we have FeCl3. How do we know it's ionic? Fe is iron, and that's a metal. Cl is chlorine, which is a nonmetal, so metal, nonmetal, therefore ionic. So again, Fe is iron. And then ask yourself, is iron a transition metal? Since it is, you'll need Roman numerals that have its oxidation number. So let's leave some space for that and then come back to it. And then jump right to the anion now. Cl, this is one type of atom. So we change the ending to ide. So instead of chlorine, it's going to be chloride. All right, so going back and finding the oxidation number of iron here. To do that, I would separate your ions. So we have Fe and Cl. And then uncross the subscripts. So this 3, we're going to uncross up here with Fe. And there's not a subscript listed with Fe, so it's understood 1. So we uncross that up here with Cl. So right now we think iron is a 3 plus and chlorine's a 1 minus. And then check the anion, because we know what charge the anion should have. The questionable ones that we aren't, or that could have variable oxidation numbers for our case, is going to be the transition metals. So ask, does chlorine really have a -1 charge? Yes, it does. So iron does have this 3 plus. Okay. So here we're going to put the Roman numeral 3 for iron 3 chloride. And you can, if you feel more comfortable going from the names to the formulas, you can go that way and check yourself. So iron 3 chloride, iron is Fe. This 3 here tells us it's a 3 plus. Chloride is Cl, and it gets a 1 minus. Crisscross or cancel. We got a crisscross, so it gives FeCl3, which is what we started with over here. Now, there is a reason that you need to check your anion's charge. So let's say, for instance, we were looking at MnO2 here. Let's say we're looking at this one. So first, how do we know this is ionic? Well, Mn, which is manganese, is a metal, and then O, which is oxygen, is a nonmetal. So metal, nonmetal, therefore ionic. So from there, I would write out the first one, your cation. So man, gan, ese. And then ask, is manganese a transition metal? It is, so we're going to need to leave room to go back and put that Roman numeral in there for its charge. And then moving on to the anion, this is the ending to ide. So we're going to have oxide. All right, so going back and getting the Roman numeral for manganese, its charge, again, I would split up your ions. So we have Mn and we have O. And then uncross the subscripts to make them charges again. So we have manganese gets this 2 plus right now. There's an understood 1 here with manganese. So we're going to give oxygen a 1 minus. And then check, does oxygen really have a 1 minus charge or a minus charge? It doesn't. It should have a 2 minus. So since oxygen should have a 2 minus instead of 1 minus, we have to double this charge here. But if you're doubling your anion, you have to double the charge of your cation. So that gives O with the 2 minus, and that gives Mn with a 4 plus. So this manganese, if you didn't check your anion, you may have written 2, but really its oxidation number here is a 4 plus. So since manganese should have that positive 4 oxidation number or 4 plus charge, and we got that from checking the charge of our anion. And again, if you feel comfortable or more comfortable going from the name to the formula than from the formula to the name, once you have what you think is the correct name, you can go backwards and check if that will give you the correct formula. So manganese is Mn. It has a 4 plus charge here. Oxygen is O. It has a 2 minus charge. We crisscross those. So Mn2, O4. And then remember, if you can reduce, you need to reduce. So we reduced or divided here, which is why we got to multiply up here when we're checking the charge to get that true charge of manganese here. All right, so that is all for this video.